So, welcome back student. So, we are basically discussing several strategies, and in the last lecture we said that we will be trying to discuss some of the starting material based strategies where the target will be given to you, and I will also give the starting material. Now, actually for these strategies we will try to have a combination of all the three strategies we have discussed together. We said functional groups, starting material and transformation are basically a combined approaches for a given target. And this particular target was pretty similar. It is a very simple target, it is a cyclohexane based compound. You are having 2 methyl here and also a tertiary alcohol. The relative stereochemistry of this hydrogen and OH is given, that basically means that this hydrogen and OH has to be in syn phase or same phase. Fine. The starting material is pretty cheap, is orthoxylene. Eventually starting material is aromatic, and this product is non-aromatic. So, normally in the synthetic transformation, if I say how many reactions can you name which basically destabilizes the aromaticity of a given aromatic nucleus, destabilizes the aromaticity. Basically, there are very few known name reactions which can allow this, and one of the classic reaction is Botched reduction, which does the tricks. Botched reduction we have earlier explained, it is basically a radical mediated or single electron mediated reduction. When you have a sodium metal or lithium metal dissolved in liquid ammonia, you will get this kind of aromatic non-aromatic hydrocarbon. Okay. Now, Botched reduction has a very unique regiochemistry. If you put a electron releasing group in this benzene nucleus after this Botched reduction, you will normally get this compound. Now, this regiochemistry we will explain a little bit later on, and if you having a electron withdrawing group after the Botched reduction, will basically explain this regioisomer. And this two regiochemistry, I mean this regiochemical issues sometimes helps to design effective synthetic pathway, that which particular aromatic hydrocarbon will you choose to access the corresponding cyclohexadiene. Or now this functional groups or these double bonds you can basically manipulate in such a way you can create a substituted cyclohexane from aromatic hydrocarbons. Now, aromatic hydrocarbons, I say aromatic hydrocarbons are very cheap, they are very cheap because they have been derived from petroleum industry. Aromatic hydrocarbon is cheap, very cheap and raw starting material, or you can call them raw feedstock. These are absolutely cheap starting material. So, you can often use those as a starting material for your synthetic pathway depending on the target structure. Now, in this particular case xylene was used as a starting material. Now, xylene, you see the xylene molecule having 2 electron releasing group in the benzene ring. So, you do a Botched reduction by sodium and liquid ammonia. So, based on the regiochemistry you will basically get this compound. Now, if you see the target molecule, now we do the retro. The target molecule is having methyl is there, here is a hydrogen having a OH. Now, what we do? We now do a retro and see how this compound can be correlated. We say if this olefin is there, you can do a hydroboration reaction, you can do a hydroboration reaction. Okay. So, it is FGI by simple hydroboration reaction. Now, this can you correlate with this to this? means that one of this olefinic unsaturation needs to be hydrogenated. The only difference is this double bond is electronically rich because it is having more methyl groups, and this is not like that, and also it is sterically less crowded. So, particularly this case you can use a hydrogenation reaction by a sterically bulky catalyst which is very well known, named as Wilkinson's catalyst. Now, Wilkinson catalyst, we are not going to talk about very detail in this catalyst. It is a rhodium based catalyst, is having triphenyl phosphine rhodium chloride. This catalyst basically helps in hydrogenation reaction, is a basically homogeneous catalyst. Now, as this catalyst is pretty bulky, it will tend to hydrogenate the olefin which is sterically less crowded or less congested. Now, this olefin is very much sterically congested. So, catalyst has to approach in this particular olefinic site, and it is very difficult because catalyst is also quite bulky. So, in this case the sterically less congested olefin will be hydrogenated. And now, basically we can explain, we all know the hydrogenation always is a synfacial. The basically the catalyst surface is this is the catalyst, and your olefin is like this. So, hydrogen will be always attacking from syn face. So, then if you hydrogenate this compound, you can basically get either this compound or you can get its enantiomer, right. Oh, sorry. So, you can these things are there, yeah, these things is there. No, this double bond is sorry. Aha. So, you will basically get you get basically this compound, and there is no chance of stereochemistry because this double bond is only reduced and there is no stereo center here, fine. So, now next what you are doing, next basically you have to do a hydroboration reaction. So, hydroboration will now try to write the olefin in this way, the methyl and methyl. Now, hydroboration is basically addition of hydrogen and BH2, and hydroboration we always say is a syn addition. So, means that you will basically having this isomer, or you may have the other isomer where methyl will be below, hydrogen will be here and BH2. So, now basically you can clip these things with sodium hydroxide and hydrogen peroxide, and you can basically get the product which is given as a target molecule. So, you can get either this product or you can get this product. These are basically enantiomer to each other. Means that hydroboration, the hydrogen and OH are seen to each other. Now, any one of these is our target molecule. So, if you can see a simple aromatic hydrocarbon is undergoing a Botched kind of reduction, and then do a simple hydroboration reaction which will now fetch the target molecule in a very systematic and efficient way. So, in the same line our next target is little bit different molecule. So, the cyclopropane is above of this plane and you have a alpha hydroxy. This is your target molecule. The starting material which was given here is having almost similar connectivity but only thing is the number of carbon everything is same. You basically have a oxygen introduced here, a oxygen containing functionality in a stereoselective way. I mean the particular stereo center is to be taken care of. The double bond, instead of a endocyclic double bond, now we are having exocyclic double bond. So, what I am trying to do, we will now follow the retro pathway, how it could be. This is a cyclopropane thing, and then we say if you having this epoxide, now this epoxide probably if somehow you can abstract this methyl hydrogen by some means, is it possible that you can do a little bit rearrangement, so that the epoxide opens up to give you this target molecule. Now, eventually this abstraction of this hydrogen seems to be bit difficult, but there are ways to do it. So, now we will try to figure it out how the synthesis can be carried out. The starting material is this. So, what we do now, we take the starting material, the first step we need to do a epoxidation. We will try to put a MCPBA, metachloropyrbenzoic acid. Now, this cyclopropyl group blocks the above phase. The olefin is like this. So, basically a steric guided or sterically directed epoxidation will takes place and will give you the beta epoxide as the major product. Means the top phase of the olefin is blocked by this cyclopropyl group as it occupies the above plane. Now, here we say that this compound, if you can treat with a base like LDA, LDA is lithium diisopyl amide. Now, is it possible that this base will abstract this hydrogen? It is possible actually, it can abstract hydrogen from here, it can abstract hydrogen from here also. Now, we will try to analyze which hydrogen will be abstracted. For this, we will now write the cyclopropane in this way in its 3-dimensional structure, and then you say the cyclopropane is here, and then you can now figure the epoxide in something like this, the epoxide, and then this epoxide you are having this particular epoxide, this particular epoxide is having this methyl, is a methyl is there, as epoxide is below, methyl has to be up. And we said that LDA might abstract a hydrogen. Now, LDA can also abstract a hydrogen from here also, because we say this CH2 might be abstracted, this hydrogen also can be abstracted, and there is a LDA is a N isopropyl lithium, this is the real base, this is the real base. Now, the mechanism basically, if it abstracts this hydrogen, then it will be something like this, open up and you get this product. Now, if it abstracts this hydrogen, this will also opens up, and in reality that will give you the another rearranged product whose structure will be something like this. Now, in reality this product also might be formed, but as we have given only one product, you can take it that if this hydrogen is abstracted, but in reality this is there is a absolute possibility that this product might be also formed. And in my opinion, if you see the particular stereochemistry here, the hydrogen which is close to the oxygen or the epoxy oxygen, it is always possibility that LDA might pick up this hydrogen and then do a this kind of thing. So, this product also might be formed, but as we did not observe it here, as the target is having this structure. So, we formulate that if this mechanism operates where a methyl hydrogen was removed by this. So, it is basically a mechanism driven retro, and in many cases sometimes depending on the mechanism or the pathway we can explain that how this retro might be possible. The next retro will trying to have a little bit complicated one, not complicated exactly, but we will explore the strategy which you already discussed before. We said cyclohexenone based target molecule was given to you. The starting material was very interesting. You are having aromatic hydrocarbon, this 3-ethyl anisole or 3-ethyl methoxybenzene. Okay. So, this was the starting material which was given to you. Now, again this will basically gives you a possibility that is aromatic hydrocarbon, chief starting material. So, initial step you need to do a Botched kind of reduction, so that the aromaticity will be disturbed. So, now this compound has a electron releasing group here as well as here. So, this compound if it undergoes Botched reduction, it will basically give you as a this product. Now, you will find that in the final compound you have a ketone. Now, if you have a anisole kind of compound, after Botched reduction you do a hydrolysis. Once you do the hydrolysis, this vinyl ether will undergo hydrolysis and will give you a enol. The enol can be instantly tautomerizes to give you this compound. Now, this compound is not the conjugated ketone, it is not the conjugated ketone. It can basically in principle again undergo isomerization reaction to the more stable keto form. But if you see the target molecule, now the target molecule, now what we try to formulate the reaction, we say that the target molecule can be accessed if you have some epoxide like this. Now, just before this slide we have explained that epoxides can easily be opened up by treating a base. Now, here you are having this hydrogens which are acidic due to presence of this carbonyl group. Now, if this hydrogen will be picked up by this base, you can generate a carbon ion and that can basically open up this epoxide to actually give you ethyl and OH, which now can be converted to the corresponding acetate by treating with the acetic anhydride. So, your entire pathway will be now formulated as this way. So, first take the starting material, do the Botched reduction. So, after Botched reduction you do the hydrolysis as explained earlier, you will basically get this compound. Now, as I said, do not expose this compound for longer time. So, it will isomerize to this alpha beta unsaturated compound. So, immediately subject it to epoxidation through a MCPBA. This electron rich olefin, instantly MCPBA use one equivalent, otherwise if you use excess equivalent, Baeyer-Villiger oxidation may takes place here. So, use this one equivalent of MCPBA, you get these things. Now, you use LDA, it will pick up this hydrogen, it will make a negative here, and then this carbon ion will get this electrophilic epoxide to quench the anion, and then it will basically convert this to alcohol, and then it can be converted to acetic anhydride by this OAC. Now, this Botched reduction, as we explained, we say that if you having a electron releasing group, this Botched reduction occurs in a different way, and it gives you a very nice non-aromatic hydrocarbon. Now, Botched reduction basically a single electron reduction. Sodium, once you dissolve in liquid ammonia, it gives you a single electron. Now, this single electron now attacking the aromatic hydrocarbon. Now, depending on this group is a OMe. OMe, though it is a electron withdrawing ability, but it is also electron releasing, and its electron releasing capacity is much more than its inductive effect. So, it will not take the electron in the ipso substitution, it will always take the electron at ortho, and then you will find that once the electron has been transferred, I will write in this way. I will first try to put this benzene in this way, and then I am transferring this electron to here, okay. And then we will try to figure it out how it is basically quenching. It basically will now leave a O methyl, this is here, this is here, you get a dot here, and you get a H, and basically this is also you get a dot here, okay. So, you get a dot here, and you this electron has been basically transferred. Eventually, the solvent is always a tertiary butanol or ethanol was always used. So, this basically this minus, actually this minus will now abstract the proton, and it will give you this hydrogen. Now, this one again will accept another electron to become again negative. Now, this OMe remains here, OMe remains here, and basically you will then take H plus from the solvent, it will give you this compound. So, if you have an electron releasing group, it always prefers the single electron attack to its ortho. Now, the next scenario, if you are having a electron withdrawing group like CO2H or carboxylic acid, I say CO2H. Now, what happened? You are taking one electron which has been generated from this. Now, this one electron is transferred to this ipso, because it is electron withdrawing group, it can accept further negative charge, and then you will find that this basically will come here, will come here, will basically put a negative charge here with this hydrogen, and then this is a this dot. Now, this negative will be accepting H plus to basically give you this things, okay. Now, this dot is there, another 1 electron will be transferring here to give you a net negative charge on this carbon. Now, this negative charge is highly stabilized through this resonance of this corresponding carboxylic acid, which we all know. And this is the main reason when you have electron withdrawing group, it can do this kind of regiochemistry. Now, the point is, as you are having a negative charge here, this negative charge can be trapped efficiently by a electrophile. Now, if you use a electrophile here, you will find that this electrophile can nicely be trapped, and you can get a carbon electrophile bond with this kind of structure. So, Botched reduction, if you do with a electron withdrawing group like carboxylic acid group, and you simultaneously treat with a electrophile like methyl halide, any alkyl halides, you can get a carbon electrophile bond here. Our next problem is basically based on this particular strategy. I say the next problem which we now designed is a spirocycle based lactone whose structure is this, and the target molecule is this, and the starting material which was given to you is a this. Okay. So, it is having electron releasing as well as electron withdrawing. So, now do the conventional retro. So, I say if you do the conventional retro, you can have this C double bond to O or H something, and then CH2, 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 OH. Just do a esterification reaction by minus water. Then just now which you have explained that if you have a Botched reduction of this kind of system and you can quench these things with a electrophile. So, basically what you need a electrophile whose structure will be a Pg is a protecting group, and then this electrophile can undergoing a carbon carbon bond forming reaction, then you remove the protecting group and do this esterification. So, now we try to do the forward synthesis. Starting material is this methyl CO2H. Do the Botched reduction first. Once you do the Botched reduction, you will basically get this compound and CO2H minus. We do not now what we will be using? We are using a alcohol protected this electrophile as a electrophile, and then you will be using this electrophile to trap this carbon ion to now get the compound CH2, 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 OTBS. Now, we are almost close. We remove this TBS group by PTSA, which you have already explained, and then you find you basically get a hydroxy acid. You just heat it with the water elimination will takes place, it is a condensation reaction, and then basically it will give you the spirocycle lactone. So, a simple structure can efficiently be constructed with the help of a Botched reduction by taking care of the proper regiochemical issues. We said that Botched reduction, if you have a electron withdrawing group, it will always give this kind of compound. In addition, this Botched reduction also having a electron releasing group. So, both the things can be coupled together, then we use a protecting group based electrophile. This compound is having a protecting group. So, everything was basically combined together in the strategies, and this kind of strategical disconnection based on starting material, functional group and transformation will keep continuing in our future lecture. So, till today, so till then just go through all the slides, try to analyze the assignments. We will see you in the next class. Till then, goodbye.